Yeah, so this is a project we're doing with between UCC and ROD in association with Construct Innovate, which is a led out of Galway. It's an Enterprise Ireland funded research centre for construction technology. So I suppose the challenge of this that was kind of set forward for us was that a lot of our infrastructure is essentially getting to the end of its service life. It was most of the kind of normal bridges that we talk about were constructed, say, post World War II, and obviously different standards have evolved over time, and so a lot of them are probably approaching the end of their service life earlier than you'd expect, and then some of them need to be kept going a bit longer. So usually when you're dealing with thousands of infrastructure assets, you kind of have to have a normal kind of or an easy to operate kind of management system, and that's kind of relied historically on kind of periodic visual based inspections, which you'd use to then identify maybe some structures of interest, to which you then go do a further kind of an analysis on, right? What happens in that scenario, though, is that some damage can kind of start to permeate and start to essentially happen in between inspection intervals, or it's the damage that can't be picked up on visual inspections alone. And it leads to situations, this is a bridge over in the US, where essentially fatigue stresses that were in this kind of a lower core distrust essentially caused this to completely split, right? And I think it wasn't seen by any inspectors, it was seen by somebody who was on a boat, a leisure craft underneath the bridge. So you kind of see that our kind of traditional ways of doing things is, it doesn't harness, I suppose, the technological capabilities we have at the moment, and it does lead to, the disruption risk, etc. So this is obviously one of the critical examples of it. The Morandi Viaduct over in Italy basically collapsed a good few years ago now, to say, under a severe weather event, which exacerbated some internal corrosions that were in the concrete stays. This is still in court. The CEO of the management company, I think they're looking for 18 years imprisonment against them. So it is a fairly kind of a critical scenario that we need to be, I suppose, using the best management and maintenance of technological solutions available to us. So typically the best tool we have for talking about these things is probability, right? And when we're looking at our usual systems and our usual, whether it's a bridge or whether it's a pipe or whether it's a tunnel or whether it's a dam or whatever, we generally all have the same basic criteria. You have an effect of something, and then you have the capacity of that thing to resist that effect, right? And generally what you're looking for is a design value of one needs to be less than the other, right? So the effect needs to be less than the capacity. Now that's the design effect, which we basically say is a factored effect, right? And using different safety factors to try and factor down the resistance and factor up the effect, whether it's load or whether it's bending or whatever, right? They come from a characteristic value. A characteristic value is, for an effect, might be a 95th percentile value, which basically means that there's a 95% chance that things are beneath that, right? And similarly for the resistance, there's a 5% characteristic value, which means that there's a 5% chance that your resistance is less than that. So you're looking for a very worst case scenario when you're designing. Now, the fact that you have that range suggests there's also mean values to this, or average values to this. And these average values are typically a lot less for the effect, for your mean valued effect, and a lot greater than the characteristic resistance, which leads to a probability distribution, ultimately. Right? And what you're then looking for when we're talking about designing or talking about maintaining existing bridges, we're essentially trying to look at what is the probability that this happens, right? It's our best tool that we have for evaluating the long life of these structures, right? So it's a very small event that we're ultimately looking for, but it does give us the best information that we have. So essentially what this becomes a data problem, right? So if you want to be able to evaluate this probability of failure, right, and give a true representation of the safety in the structure, you need to have the data to be able to generate these probability distributions. So how do we generate that data? Structural health monitoring is I suppose the main way we do it. Typically it just involves rigging up a structure such as a bridge with sensors. It's no real difference to The heart rate monitors you might see on soccer players, rugby players, the only difference is that they're being monitored in real time of their infrastructure assets are being kind of monitored after the effect, or they're being looked at after the effect. But it basically allows you to analyse various different types of movement and change in the structure to be able to determine what's happening. It does allow you to take all this data and use it effectively, right? The problem that we have largely to date is a lot of this monitoring is done on almost like a purely academic basis. It's been done to advance academia and advance research as opposed to actually manage structures. In the structures that it is being implemented on, it often results in what some asset managers call a data lake, in the sense that they have the data, they don't do anything with it, right? So it exists, but they're not doing anything with it. So what we're looking for is some system that allows you to take this structural health monitoring and actually implement it into real world practice, right? So the digital twin is essentially the next step in this, right? So we're all familiar with our modelling in 3D, whether it's a BIM model or it's a physics-based model, such as final element model, and what we're trying to create is a physical representation of the structure, right? From that then, we can use our structural health monitoring to essentially tell us what's happening with that structure in real time and get a general feedback loop into how we can see what is happening, what stresses are under the structure is being subjected to, how it's moving, how it's responding, right? It does create this two-way connection, right, in the sense that we're getting information from the structure, we're feeding it into the model, we're refining the model, we're being able to plan future interventions into the model, and then we can model from that how any future strengthening work is actually going to impact the bridge, so that we can come up with an effective and a cost-effective way of doing that. A recent good example of this is the Hamburg Smart Bridge, where essentially this is a bridge over the Port of Hamburg, rigged it up with a lot of sensors, had a real-time mobile or web-based platform that they can see what was happening in the structure, depending on whether it was subjected to abnormal traffic loading, extra wind, temperature variations, etc. Right? The problem with this is that this project has come to an end and they're just replacing the bridge anyway. Right? Mostly to do with the fact that there's height restrictions on it. But this is I suppose the genesis of the idea for the Prodigy project that we have with already in constructed on it. So the idea of the digital twin, the idea of structural health monitoring, and the idea of probabilistic analysis, it all comes in and all fuses into this one probabilistic digital twin idea, where essentially the structural health monitoring system are the senses, right? It does what's going on. The digital twin is the body, where we can actually see, or we're actually able to analyse this, to look at this, whether it's a BIM model, whether it's a physics-based model, as I said. And then your probabilistic methods are the brain, which tells you what's happening, what might happen into the future. If a various bunch of different things were to happen, how would this manifest itself, right? So it allows you to ask the critical question of what is the likelihood of a future problem, especially in the context of climate change. If we have increasing storms, is there going to be a knock-on effect then into your infrastructure, right? So the whole thing has this kind of continuous learning loop where we have the physical asset of the bridge. From this, we can create a physics-based model for the most part in order to process the actual effects in the structure. We have our sensor data, which is from our strain gauges, our tilt meters, our temperature gauges, and then we create the digital twin, right? So the digital twin then allows us to compare and learn as to what is happening in the bridge against what's happening in our models, right? So if we create a model of a structure, and we anticipate a response, and then we monitor the structure, and we're getting a different response, we know the structure's right, the model's wrong. So we have to calibrate the model, we have to update the model. So that's where the compare and learn kind of scenario happens to this. And this is what we're mostly focusing on at the moment within this project. Once that's kind of bottomed out, we get to go on to the probabilistic phase, which allows us to look at then how is the structure responding, what is the likelihood of failure, what is the risk associated with that failure, and into the future, if we can plan for future deterioration and how that will affect that probability of failure. And then finally, a decision and action where we can forecast into the future. If we strengthen now, what kind of a residual service life will we get out of the structure? If we strengthen later, what will happen? So we kind of essentially have a technology ecosystem here. So it's not one software, it's not one tool, it's essentially a system where we have a perception layer, which is essentially going to be driven by your sensor data and your geometric scanning. And from that then we have our LiDAR, our drones, we can create that physical model, right? An accurate physical model that we're not basing on as-built drawings, we're basing it on reality, right? We have a common data environment in our physics-based model. That's our integration layer. We have a connectivity layer, which is processing all that data, which we need 5G technology or edge computing. And then we have the analytical layer, which is where the AI and the machine learning comes into place. Machine learning is important for being able to create surrogate models so that you're not running a finite element simulation over and over and over and over again. So the Prodigy project then, I said we're kind of early stages in it, but we've created a series of physics-based models for an existing overbridge on the motorway network. We have existing data for it to calibrate the response to the structure to load testing that was previously done, and at the moment we're in that compare and learn stage that we can use to actually create that physical, accurate and high fidelity representation of the model. The main challenges that we're having with it is that computationally it's quite inefficient, right? When you're doing this probabilistic analysis, even for a simple structure, you can get into days worth of computations. So we can need to look at cloud-based and data cluster technology. What is the digital thread? How do we get the innovation to go from the data to the physics-based model to the probabilistic model? And then how do we validate that model against real-world data? As I said, the old saying of all models are wrong, some are useful, and then some are more useful than others. So that's what we're trying to do. We're trying to get a useful model that allows us then to accurately program into what the future responsive structure is going to be. And it does create a skill gap that we're not probably doing in universities the way we should be doing, but it does blend civil engineering, IT, and data science. So basically the future of it is we have a predictive twin. That's what we have today, right? All the information we have, we can create a predictive twin what can happen. We've a near future scenario, we've a prescriptive twin, which is telling us what's going to happen and what you should do about it. And then we have the cognitive twin, which is the long-term ambition, whereby based on all the information you're feeding into it, it not only will tell you what you should do about it, depending on robotic technology, it might be able to do it for you, right? Bit pie in the sky, but that's essentially where we're heading for. And then this network level digital twin, where you can evaluate cascading events in critical infrastructure to see if, various different bits of infrastructure, if they fail, will they fail, and it can be cascading way. So that's basically the project. It basically analyses and puts forward this idea that we need to be looking at structure or infrastructure in a smarter way, using probabilistic analysis as the intelligence. Then we can go from a kind of a reactive system to a kind of a living kind of prognostic engine over time to use risk-informed then decision-making to better improve our infrastructure management. Thank you very much.